Okay, now let's talk about sample size for an interval estimate of a population mean. Sometimes we may have our standard deviation and our z-value and our margin of error, but we want to derive n. In fact, this formula here is just a reconfiguration of this one, solving for n rather than margin of error. So this is the formula in which we will plug our information in to solve for the sample size. The necessary sample size equation requires a value for the population standard deviation, right there. If the standard deviation is unknown, a preliminary or planning value for the standard deviation can be used in the equation. Use the estimate of the population standard deviation computed in a previous study. Use a pilot study to select a preliminary study and use the sample standard deviation from the study, or use judgment or best guess for the value of the standard deviation of the population. Let's practice this. It says, suppose admissions and records would like to know the amount of time it takes freshmen to register for classes. They would like to be 95% confident that their estimate is off by no more than 2 minutes. How large a sample will be required if it is known from experience that 18 is a reasonable value for the population standard deviation? Well, first, let's go back to the formula so that we have it handy. We know that the necessary sample size is going to be equal to our z-value squared times our population standard deviation squared divided by the margin of error squared. Okay. So with that information, we can start to plug in some numbers. It says they would like to be 95% confident. Well, 95% confident turns out to be a z-value of 1.96. And you can see that in the table. If we go back to our table here, find 0.975, which is right here, and you have 1.96, okay, 0.975. And you're using 0.975 because remember, in our illustration, what we're trying to do is leave a total of the alpha in the tails. Well, here, if we want 95% confidence interval, then we need 0.025 here and 0.025 here. The sum of these two equal 5%, and that means the remainder between these two is 95%. But when you go to the table, you're looking for the z-value that corresponds from the left tail all the way up to here. Well, this is 0.975. So we look for the z-value that corresponds to 0.975, and that's 1.96. And since it's symmetrical, it's negative 1.96 as well, which is, if we had started over here on the right and went all the way to here, we'd have 97.5% in this part of the bell curve. All right, so 1.96. Of course, we need to square that. And then we're going to multiply that by the population standard deviation. And that is given to us at 18, right? Large sample will be required if it is known from experience that 18 is a reasonable value for the population standard deviation. So we're going to put 18 and square that one. And then for our denominator here, we need the margin of error squared. And it says that they would like to be 95% confident their estimate is off by no more than 2 minutes. We're going to put 2 squared. Now, once you have that, we can go into Excel and just use it as a calculator. Right? Let's see, we need to calculate the numerator. So we put equals 1.96, and we can square that. So squared, and then we're going to multiply that by 18 squared, and then we're going to divide that by 2 squared. Okay, and then hit enter, and the answer is 311. So n would be equal to about 311 people. Okay, next let's move on to the sample size for an interval estimate of a population proportion. Okay. So before we did this for the population mean, And now we're going to do it for a population proportion. The margin of error, you'll recall, for a population proportion is E equals the z value times the square root of this here, which is the probability of a success times 1 minus the probability of a success divided by n. Now, if we rearrange this margin of error formula to solve for n rather than e, we get this. However, P bar will not be known until after we have selected the sample. We will use the planning value P star for P bar. In essence, if you're going to do a research project, you don't know what your proportions are going to be. If you go out and collect a sample of people based on, smoking, and you don't know if 20% of those people are going to smoke or if 30% of those people are going to smoke, you don't know what the success is going to be until after the fact. But you need to select your sample size before the fact. So what we do is we use a planning value, which is just P star, but it's the same formula. And the P star can be chosen by one of the following procedures. One option is use the sample proportion from a previous sample of the same or similar units. 2, you could select a preliminary sample and use the sample proportion from this sample. 3, you could use judgment or best guess. What do you think it's going to be? Otherwise, use 0.5 as the p-value. All right, now let's go ahead and practice this. It says, it is known that no more than 30% of all voters in a district agree that all drugs should be legalized. A local politician would like to know the true proportion of voters who agree. How large a sample is required if a politician would like to be 95% confident that the estimation is off by no more than 4%? Our formula for this type of question is going to be n equals z squared times p bar times 1 minus p bar divided by margin of error squared. We just plug in our numbers. Okay. We know z that corresponds to a 95% confidence interval is 1.96. We did that in a previous example, so we don't need to do that again. We know that the p bar is going to be 30%, right? Because it says knowing that no more than 30% of all voters in a district agree. So we put 0.30, and then 1 minus 0.3. And we can divide all of this by our margin of error, which it says confident that the estimation is off by no more than 4%, so 0.04 squared. Now, if you do this in Excel, let's pull this up here. Let's see what we get. Well, 1.96, we want to square that, and then we're going to multiply that by 0.3. And we're going to multiply that by 0.7, right? Because 1 minus 0.3 is 0.7. Then we're going to divide this whole thing by 0.04 squared. Looks good. And the answer that we get is 504. So we would need to collect 504 people for this sample. The next one says, an official of an insurance company would like to know the proportion of the time pharmacists fill a prescription with a generic drug when the doctor does not specify a brand name. The official would like to be 95% confident the estimate is not off by more than 4%. What sample size is required? We'll be using the same formula. Let's plug in what we have. N is going to be equal to z squared. Well, we already know z because it's the same confidence interval as up here. So it's going to be 1.96 squared. Then we're going to multiply that by p bar times 1 minus p bar. Well, up here, we knew the p bar. Down here, we don't. So let's look at what options we have when we don't know p bar. Option 1 is use the sample proportion from a previous sample of the same or similar units. This might be a good one if we're repeating a past study. However, there's no indication in the question that that's occurring. The second option is to select a preliminary sample and use the sample proportion from that sample. Now, that's possible, but it does add to the cost and time frame under which the study is taken. 3, using judgment or best guess for a p-value. This, of course, would be the least credible, but may be appropriate if we can get close with a guess to the actual p-value. The question we have about the proportion of time pharmacists fill a prescription with a generic drug when the doctor does not supply a brand name, that one, there's no best guess that we could do with that. Maybe if we were a pharmacist, we could, but from the outside, that would be a tough one. And then 4, use 0.5 as the p star value. So we're going to do that one as kind of the default. Okay, so we have the z. Now we're going to put for our p bar 0.5, and then we want 1 minus p bar, 1 minus 0.5. We're going to divide the whole thing by the margin of error squared. And here it tells us the official would like to be 95% confident the estimate is not off by more than 4%. 0.04, square that. Now, going into Excel as our calculator, we can do our computation. So what we're going to do here, we're going to put equals 1.96, and then we're going to square that. I'm going to multiply that by 0.5, and multiply that by 0.5, and then divide the whole thing by 0.04 squared. Now, if we do that correctly, we get 600. So n equals 600. We would need to select about 600 people for this study. Okay, now let's use Excel to create confidence intervals. It says a random sample of 18 families found that they sent an average of 44.7 greeting cards during the holiday season, finding 98% confidence interval for the mean number of cards sent by the population the sample was taken from. The sample's standard deviation is 8.1. Find the maximum error of the estimate using Excel's confidence T function. And we can use the T function here because we're dealing with a sample standard deviation. So we put equals confidence dot T, pull up our argument box. Our alpha here is going to be 0.02 because it's a 98% confidence interval. Our standard deviation is given to us for the sample of 8.1, and our sample size is 18 families. If you do this correctly, you get 4.9. That means the true population range is going to be 44.7 greeting cards plus or minus 4.9. Now we can do the same thing with this question down here. A random sample of 75 students taking the quantitative exam at SDSU showed an average score of 18.3 with a population standard deviation of 5. What would be the 95% confidence interval for the estimate of all scores on the quant? Find the maximum error for the estimate. Use Excel's confidence.norm function. Now, in this case, we're going to put equals confidence, but we're going to select this one. And the reason is because we know here the population standard deviation. So we don't need T, we need Z or norm. Our alpha is going to be 0.05 because we have a 95% confidence interval. Our standard deviation for the population is 5, and our sample size is 75 students. Do this correctly, and you get 1.13, which means we believe, based on this sample, that the true population mean is 18.3 plus or minus 1.13. We could also create that 95% confidence interval. Simply take the mean, which is 18.3, and then add to it the 1.13, and that gives us the upper confidence level, and then take the mean, 18.3, and subtract from it the margin of error. So we believe the true population mean is between 17 and 19. All right, that's it. Thanks.